So we learned earlier in the course that if we've got a random variable x and we want an expression for its variance, okay, well, with the sort of the default formula, the standard formula is to say, okay, well, this is just going to be the expected value of the squares of the distance between x and its expectation, okay? And we could replace this e of x here with mu to mean the mean of x. This is sort of the way the variance is defined. And we also learned along with this formula, sort of a more useful formula, one that's more practical to use. And this is, we can express the variance as the difference between the expected value of the square of x, so the e of x squared, and the square of just the expectation of x. And so we're just computing the expectation of x, and then we're squaring the whole thing. Okay. And so this is sort of a condition for the population, because we're looking at the random variable, which represents the full distribution of our data. And this is a great condition for the population. And what we want to try and do is build up a similar condition, something that's sort of computationally useful for the sample variance, And so let's start off on this task by writing out just the formula for the sample variance. And remember, we express the sample variance of x as s subscript x all squared, in contrast to how we express the population variance, which is sigma subscript x all squared. And we can write out the sample variance as 1 on n minus 1. Remember, correcting, we lose a degree of freedom. Multiply it by the sum from I equals 1 to n of xi, which is a particular value of our variable x, minus x bar, which is the sample mean of our variable x all squared. Okay, so this is sort of how we define the sample variance of a variable x. And what we're going to do is we're going to rearrange this so it's just a little bit more useful, okay? And the first thing we're going to do is we're going to rewrite this square as literally is the product of xi minus x bar with itself. Because after all, that's what we say, that's what we mean when we say xi minus x bar squared. Okay, and we're going to do a second step. We keep this 1 on n minus 1 the same. And in our second step, we're just going to rearrange. We're going to rearrange everything inside these brackets. And it's just a product of 2 brackets. It shouldn't be too hard. And first we've got xi times xi. And so that's xi squared. And the second term we have is minus x bar times minus x bar, which is just plus x bar all squared. Okay. And then we got xi times minus x bar plus minus x bar times xi, and so we're going to get 2 times minus xi times x bar. Okay, this is the first step. We've just expanded these brackets here. And what we're going to do now is we're going to apply this sum separately to each of the terms here. Okay, and so we're going to write out the first term is going to be 1 on n minus 1 times the sum from I equals 1 to n of xi squared. And so we can't really simplify this. This is just our data squared. This is a relatively difficult thing. We can't really simplify this. And the next term is going to be, okay, the sum, just applying the same sum to the second term here, from I equals 1 to n of x bar squared, okay? And we're going to have a third sum. We're going to take minus 2 at the front. We're going to have minus 2 times the sum from I equals 1 to n, just the same sum applying to each of the terms in the sum, of x bar times xi. Okay. And so we can sort of inspect each of these terms and ask ourselves, okay, can I simplify this expression here? And we can't really simplify this one. But have a look at the second term, and we'll see that just the sum from I equals 1 to n of x bar squared. Now notice that this sum indexes over I. And so anything that doesn't relate to I, okay, isn't really going to be affected by this sum. It's not going to change. And so this sum is going to be, okay, for I equals 1, it's going to be x bar squared plus, and then I is 2, and it's just x bar squared again. And so what we're going to get is just n copies of x bar squared. And so we can replace this sum with just the number n. Because we're going to get n copies of x bar squared. Okay. And we look at this third term here, and we notice that, okay, x bar doesn't depend on I, and we can actually bring it out the front, just like we brought minus 2 out the front. And all that's left once we bring x bar out the front is just the sum from I equals 1 to n of xi. Okay? And we'll remember, if we take the sum from I equals 1 to n of our data and divide it by n, we get the sample mean. And so if we take the sum from I equals 1 to n of our data and we don't divide it by the sample mean, what we're going to get is n times the sample mean. N times the sample mean. And so we can rewrite this as minus 2 times the sample mean times n times the sample mean. So we can just quickly rewrite this equation here. So we're going to get minus 2 times the sample mean, like we said before, x bar, times n times the sample mean. Okay? And we can just rewrite this one more time very quickly. We notice this is going to be minus 2n x bar squared. Minus 2n x bar squared. Okay, so we've got a long way to simplify this expression. And sort of one final thing we want to notice when we're rearranging this is that, okay, well, we can't really simplify this first term here, and we've simplified the second and third terms sort of as much as we can. But we can combine now, we can combine these second and third terms because we've got plus 1 times n x bar squared minus 2 times n x bar squared. And we have 1 times something minus 2 times something. What we're going to be left with is just minus 1 times something, just minus 1 times something. Okay, so we've got this first term, the sum of xi squareds, minus, notice this isn't in the sum, minus n times x bar squared. Okay, so this is going to be our final equation. And so if we compute, or someone gives us the sum of all the squares of our data, we can quite simply compute what the sample variance is going to be by just having 1 on n minus 1 times that sum minus n times the sample mean, which is quite easy to compute, all squared. And we can see here there's quite a nice parallel with this equation up the top, because with our first term here, we've got the sum of all our xi squareds divided by n minus 1. That's sort of like the expected value of x squared. And in our second term, we've got minus n divided by n minus 1, which is very close to 1, times x bar squared, which is sort of nearly the expected value of x squared. And so the only difference we've got here is these sort of little corrections that we've had to make, because this is not the population variance. This is not the population variance. This is the sample variance. And so we have to correct by this term out the front here, n minus 1.